You may wonder how the derivative rules that you may have learned before or that you're learning now in class connect to this definition of the derivative that we've also discussed involving this limit. And the thing is, you can actually prove most, if not all, of these rules using that limit definition. So let's go ahead and go ahead with some of those. So we're going to start with the constant multiple rule because it's one of the easier ones to show. So if I want to show what the derivative of the function k times f of x is, let's say I know the derivative of f of x. What is the derivative of k times f of x? Well, let's just go ahead and start by writing out our limit definition. So this is going to be the limit as h approaches 0 of k times f of x plus h minus k times f of x over h. Well, look, both of these are being multiplied by k, so I can go ahead and factor out that k. I don't want to factor it out that much. I will eventually, though. That's the same as the limit as h approaches 0 of k times f of x plus h minus f of x, all of that over h. And one rule that we have with limits is that if you have something being multiplied together, you can take the limit of each of those separately. So you could think of that as the limit as h approaches 0 of k times, well, we'll go ahead and write it. The limit as h approaches 0 of k times the limit as h approaches 0 of f of x plus h minus f of x over h. Often we won't write it out like this. We'll just say that we can pull out a constant multiple with limits. So we could have had just skip to this step where we say k times the limit as h goes to 0 of f of x plus h minus f of x over h. And lo and behold, this is the derivative. At least this limit as h approaches 0 of f of x plus h minus f of x over h. That's the derivative. So this is just k times the derivative of f of x, which is exactly what we know from the constant multiple rule. If you take a function and multiply it by some constant, you can take the derivative by taking the derivative of the function and then just multiplying that by the constant. So you can basically pull the constant out, ignore it, and then multiply it back in. So that's nice. We can do a similar trick with the derivative of f plus g of x. So really what I'm doing is I'm taking the limit as h goes to 0 of f plus g of x plus h, minus f plus g of x all over h. And that's really saying the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x, I'll put these in parentheses, minus f of x plus g of x, all of that over h. And then we can split that up into two parts. Before we split it up into two parts, let's go ahead and distribute that negative sign. That's going to be the limit as f of x plus h plus g of x plus h minus f of x minus g of x all over h. I notice that I have some f's and I have some g's. I'd like to put the like things together. So this is going to be the same as the limit as h approaches 0 of f of x plus h minus f of x plus g of x plus h minus g of x, all of that over h. And I can split that up into two pieces. That is really the limit of f of x plus h minus f of x over h plus g of x plus h minus g of x over h. Now, another one of my rules for limits is that I can take the limit of each term. So this is really the limit as h goes to 0 of f of x plus h minus f of x over h plus the limit as h goes to 0 of g of x plus h minus g of x, don't need that parenthesis, all over h. And what are those two things? Well, this is just the derivative of f of x, and this is just the derivative of g of x. And that's exactly what we would expect from our addition rule for the derivative. So we've taken these two basic derivative rules and actually shown that they're true using the limit definition of the derivative.